This is how we define current density. We consider a wire. Let A be the cross-sectional area of the wire. So we have some kind of a perpendicular cross-section of that wire, and A is the area. So the ratio of the current to the area is called the current density. Okay, so it's a density per area. So from this expression, it can be seen that it's quite easy to write that the current is current density times the area. Now, if we just look at this expression, let's remember that in the past we have seen that area can be interpreted as a vector. It's a vector perpendicular to the surface that it expresses the area. We have just seen that the current is a scalar quantity. So therefore, if I interpret current density as a vector quantity, then I can write this down as a consistent vector equation, like current is equal to the dot product of current density with the area. So the nice thing is that I can generalize this, okay? But let me go back to the definition. So this definition of current divided by area just gives us the magnitude of the current density. And in addition to that, we had to define a direction. So the direction would be the same as the direction of that arrow, actually, that we measure the current. So as a result, J has the same direction as the arrow used to measure the current. Okay, so it's a vector quantity that has this magnitude and this direction. So as a result, we are going to interpret as a vector quantity. And in that case, the current can be expressed as the dot product of the current density with the area. So there's a dot product in here. In a way, this is the flux of the current density through that cross-sectional area. So that interpretation gives us a room for generalization. So let's consider this situation. I don't have to cut the wire by a perpendicular surface. I can cut the wire with a slanted surface like that. In that case, the magnitude of the surface areas would be different. This area of that cut and the area of that cut are different. So the area vector in here and the area vector in here, they are going to have different magnitudes. But we know that we have seen this in the past, that for this case, for example, this area vector has a component parallel to the wire, which is given by, if you just consider this as a vector, this vector is the same as this vector in here. So I'm just going to write it down like this. Let's say that this angle is theta. Okay, so I can express the current in here as the dot product of the current density with this area. Okay. And if this wire has the same cross-section all the time, the current density at that location would be the same. It would be the same vector. So therefore, the current in here would be the dot product of that current density with this area. But now you can see that this is the same as the magnitude of J, magnitude of A2 multiplied with cosine of the angle between them. But we have said that this is the same as A1, so therefore the current value that you get in here would be the same as the current in here. Okay, so this is a wire that carries the same current at all points. So since it has the same cross-section, it has the same current density, we can choose the cross-sectional areas in different ways, but in each case, this dot product should produce the same current value. Okay, so next, we might have situations where the wire might have different cross-sectional area. So perhaps a thin wire is connected to a thick wire. So they continue like that. So let's say that these are perpendicular cross sections. So the area in here is A1 and the area in here is A2. So the current density in here would be, let's call it as J1, and in here would be J2. This is J2. So let me also show these directions as in here, show the arrows. So the current at that point would be J1 dotted with A1. So if you want, in terms of the magnitudes, this is going to be the products of the magnitude multiplied with the cosine of the angle between them. So that's J1A1. So the current in here would be J2.A2. The current should be the same. The current should be the same. So therefore, I'm writing the same I in here. So in that case, this is again, I'm assuming a perpendicular cross section in here. So therefore, this is going to be J2A2. Okay, so this tells you that since A2 is less than A1, but the products with the current density should be the same. Sorry, it's just the opposite. Since A2 is bigger than A1, the current density J2 should be smaller than J1. So if the same current flows over a thicker wire with a larger cross-sectional area, then the current density in here would be smaller. Okay. So there are situations where the wire is kind of very non-uniform and things like that. We don't usually meet these kind of situations, but in reality this might happen. So as a result, in these kind of situations, you might have situations where the current density may also depend on the points in question. So we might have the current densities like that. So at different points, the current density itself might be different. So this enables us to interpret this current as a density as a microscopic quantity, because it just changes from point to point. So it's a location dependent quantity. So let me use a red color for drawing some kind of a cross-sectional surface. So it can be like that, right? There's a cross-sectional surface like this. Let's just draw it like that. So as a result, in this kind of a situation, I cannot write down the current as simply as current density dotted with the area. I need to do an integration in here. So it's the current density dotted with the differential area. So that means I have to somehow divide this surface into small pieces. For each small piece, I need to compute the differential area of that small piece, take the dot product with the current density in there, and so as a result, find the current that crosses that small piece and integrate. So therefore, this is just the flux of current density. So the current is really the flux of current density. So that's the current. Okay, you can think of it like that. So the things that we have said about the electric flux also somewhat valid in here. Just notice that, of course, this is not a integral over a closed surface, so we don't have an O sign in here. This is an open surface. So as a result, this quantity can be anything.